So now I'm going to tell you, very exciting, there are 3 ways to do mechanics, and you've done the hard one. That's good. So let's just take a big picture view here for a second. Big picture. One way is forces, right? So that's what we've done for 6 weeks. We've done forces. And forces are good for what? The detailed kinematics. Because that's what you really love. You want to know the angle of the trajectory at every possible point in time, and when's it going to hit the pyramid. That's what you get from forces and doing the exact kinematics. And that's the hard, most mathematical one. Now we're going to do momentum. In principle, any problem you solved in the first 6 weeks, we can now solve with momentum. But these different methods are good for different things, right? So momentum is good for collisions and interactions. So if you have, you know, the thing where you're on a trampoline with another person, and if you hit right before they hit, it throws them way up in the air. I don't know if y'all are allowed to be on trampolines anymore, but if so, you would solve that with momentum rather than with forces. 3, energy. Energy is another way to solve mechanics problems, and it's good for problems where you just know what's going on in one state, and you want to know what's going on later. The thing started here, and it got to here. How fast is it going here? I don't care what happened in between. I just care about here and here. Then that's an energy problem. And of course, in reality, we mix them. Right? We'll have problems where you do this part with kinematics, then you use your momentum here. But really, they're all 3 doing the same thing over and over again, really. So we'll show you the connections between them as we go. Okay? So today we'll start with momentum. So let me just start out by just simply defining momentum. And we'll talk about it, and we'll do some practice problems, etc., etc. Let's see. So momentum. Momentum is simply mass times velocity. So no new physical concepts to think of, just multiply 2 the concepts we've already talked about. We describe it with a little p equals mv. That's it. I really had to stretch to get 70 minutes out of this today, okay? But I've got it here. 70 minutes of, oh, never mind. Okay, so things to note about momentum. It's a vector. 70 minutes of heaven, that's what I was trying to think of. It's a vector, right? Just like if velocity is a vector, momentum is a vector. It's unit. What is its unit? Oh, we're good at units now. Kilogram meters per second. Its unit has no name. So there is the opportunity. If you do something major in momentum, we might name the unit after you. And then finally, we want to think about Newton for a second. Okay? So everybody get out your Principias and turn to page LVI. If you didn't bring your Principia, here it is. Okay? This is the actual book that Newton actually wrote, and this is what he actually said when he said his 3 laws. Here it is, right here in Latin. He wrote it in Latin because back then, anything important you did in Latin. Today, it's like when physicists do their papers in latex. It's the same thing. They think it's more important if they did it in latex instead of Word. So we got to read it. Oh, it's hard to see. Here you go. Here we go. It's in Latin. Does anybody here speak Latin and want to come down and translate it? I know you guys are like deathly afraid of coming up here, but you're also, anybody that knows Latin, I mean, this is your one chance in your entire life that it's actually going to be useful. And usually people get very excited. At least one of you went to some school that taught Latin. No? No Latin nerds here? Okay. All right, well, let's do it the hard way. Law 1, corpus omne perseverare in status suo qui scient. No, okay, let's translate it. Last chance? You know you want to. Okay. Everybody perseveres in its state of rest or of uniform motion in a right line, unless it is compelled to change that state by forces impressed thereon. So that's the closest translation we can get, or that's the most accurate. So what I want to show you is that Newton was actually talking about momentum. And also the second law we'll do, he wasn't really being real specific, and his math was different from our math. But if you want to go conceptual, what he really means in the first law, an object at rest will remain at rest, an object in motion will remain in motion, its state of rest and its state of motion. Really, the laws are more about momentum than they are about forces and accelerations. Okay, so that's what we're going to see as we go through and think about Newton. Okay, so another thing about momentum is it was Newton's, you could interpret, state of motion, which already tells you things about it that we're not getting to until Thursday, like that it doesn't change, right? All right, so now we're going to demonstrate momentum. Do office hours change to accommodate fall recess? I don't know. Let's see. I'm not sure. We haven't thought about that yet. You guys are way ahead of us. Okay, I'm going to demonstrate momentum. Here we go. I'm a mass, and here I'm going to have velocity. Ooh, so I have constant momentum if I'm not slowing down. Momentum. Ta-da. I'm going to calculate. I got to get back over here anyway. Whoa, shit. Woo. Oh. You see, you let the board hit, and it sounds like you crashed. That's how it works. Okay. So here we go, momentum. Here's the crash card, and here's me. Whoa, shit, whoa. Okay, so let's calculate one momentum. It's pretty easy. Okay, so we want to say P equals mv. I mean, the cart weighs a little, so I'm going to go 80 kilograms. A long weekend. And I was going roughly, let's say, 3 meters per second. Right? 80 kilograms, 3 meters per second. Whoops, I better move that. Equals 240 meters per second. I think you could have done that calculation. But the main thing to remember is that momentum is a vector. Yeah, that's not the answer, right? That's just the magnitude. Momentum is a vector. So let's make x that way, y that way, and say, oh yeah, we did call it a vector, so we need an I hat on here. It's in the x direction, 240 kilogram meters per second in the x direction. Of course, right? Kilogram meters per second. Okay. I'm going to need you guys to really pull it together for Thursday, because Thursday I need somebody to come up here and be on these with me. Okay, the engineers do it. You can do it. One of you, like, really focus for 2 days and see if you can get it together enough to come down here and write on one of those. Okay. When will the test be graded by? Somebody just got here. Wednesday. We're going to grade it Wednesday afternoon. Okay, so really that's why I say what else can I say? There's not much else to say. That's momentum. That's how you calculate it. So now we've got to talk about how to use it a little bit. So, let's see. Better put it here. Okay, so the other important concept is impulse. And I'm sure if you had high school physics, you've heard of impulse and the impulse momentum theorem. Impulse is just a change in momentum. And it is literally a momentum. It is the same units. We call it J, big J. It's also a vector. It's the same units, and it's in kilogram meters per second. If we were treating it like velocity or position, we'd just call it delta P. It is just delta P. But for some reason, it's so fundamental, since it has to do with Newton's laws, we give it its own name and call it impulse. Okay? So what we want to do is look at how we can calculate this, or what it's related to in terms of the forces that create it. Right? A change in momentum, J, it must take a force to make it. So let's sort of derive a little bit here. Let's start with velocity, with the velocity-acceleration relationship. And we're going to do it 2 ways, because some of you like calculus, like 2 of you like calculus, and the rest of you don't. So let's do constant acceleration. So if you had constant acceleration, thinking back to kinematics now, we had that delta V equals acceleration times delta T. Right? If you say, wait a minute, in kinematics, there were only 2 equations. There was x equals x naught plus VIT plus 1 of AT squared, and V equals V naught plus AT. Well, this is V equals V naught plus AT, right? V naught minus VI brings it over here. That's what that is. If you have what I'll put in physics, we like to say in general, if A is not constant, in any case, the delta V would be the integral from T1 to T2 of A, which might be a function of time, dt. There's a scary version there. If a is constant, then it just becomes, you integrate at, t2 minus t1 is delta t. There you go. But if a is going to change on you, which it is in collision problems, but we have a way of blowing that off, then you got to deal with it. Okay? So part 2, multiply by the mass is all we got to do. Multiply by the mass, and you say, what? M times delta v. Well, mv we know is p. Right? So we get that delta p is mass times acceleration times delta t. That's a crappy t there. All right? And over here, multiply through by m. Delta p, this thing. Oh, it's the integral from t1 to t2 of mass times acceleration times dt. Interesting. All right? And number 3, step 3, use the force. Yes, that's clearly a force there. Insert your own Star Wars joke here. You've all seen the coffee cups and the t-shirts. May the F equals MA be with you. I do not need another one, if you were thinking of getting me one. So, I think it's funny. I laugh every time I read it. But I've got many, many coffee cups and t-shirts that say that. You can get me something else. That's okay. We're grading Wednesday. Okay. So we're going to use force here, and we're going to realize, oh, delta P is just J. All right? So J equals delta P. But now we say, oh, well, that's just the force. F delta T. Okay? So we just kind of went from some basic kinematics. Multiplying by m kind of makes it physics. And that's how we see that this impulse, in addition to being the change in momentum, delta p, it's equal just to the force applied times delta t. Now, if the acceleration was constant, that would also imply that that force is constant. All right? What if the force isn't constant? Well, then we come over here. Then we say this j also equals delta p. We could say it's the integral of the ma of the force over time. Right? I know this might be getting too low. F dt. Okay? So these are kind of the equations, the ones you would use here when you're dealing with impulse. You either multiply a constant force times a delta t, or you integrate to get force's total change over delta t. Right? Okay, so now we have it defined. Now what are we going to do with it? Okay, so we're going to look carefully at impulse, and there's another book. So Newton's book is about momentum. I actually found another book about impulse. Here it is. It's called Impulse, and it's by Stephen Gould. Scent has a secret. Okay, she lives in isolation with her parents. Okay, that's not really possible. Let's keep going. Isolation with her parents, hiding from the people who took her father captive and tortured him to gain control over his ability to teleport. Okay, it's sci-fi. Okay. And from the government agencies that want to use his talent. Sin has seen the world, but only from the safety of her parents' arms. She's teleported more than anyone on Earth, except her mother and father. But she's never been able to do it herself. Her life has never been in danger. Until the day she went snowboarding without permission and triggered an avalanche. When the snow and ice thundered down on her, she suddenly found herself in her own bedroom. Boom, she teleported. Oh my God, I have got to read that book. That was the first time. Okay, so what we're going to do is we're going to go through what happened to Scent up until the moment that she teleported, okay? And we're going to do that as the problem. If you're ever giving a presentation and you need to fill in a little something or other, take the subject of your presentation, put it in Amazon Books, and you'll have a good 30 seconds, okay? You can also do movies. I did movies, but they were a little too spicy for 125, if you know what I'm saying. Movies called Impulse were kind of a problem. Damn it, so close. Okay. Fuck. Okay, so here we are. We're going to do this as a sample problem to think about Scent. So here we go. So here's Scent on her, I didn't mean to make it like a bobblehead thing, on her snowboard. And here's the avalanche. Oh shit, here it comes, right? And it's coming that way. Right? This will get to some real physics in a minute. So what's going to happen? Right now, Scent is just going at her initial velocity. Right? She's going along, the avalanche is behind her, nothing's happening. And then the avalanche is going to push her. A big avalanche here sent right on the edge of it. Right? So that there's a force of the avalanche on scent. Right? And we know what forces do. They accelerate things. So her velocity is a little bit bigger. And then, eventually, the avalanche dies down. Right? It sort of falls down. And now scent is going V final, much faster. Oh, God. Right? And here's the rock. Oh, no, she's going to hit the rock. But don't worry, she'll teleport. And she'll be back in her bedroom. It'll be fine. Okay? So what we have is the avalanche pushes scent with force F for time delta t. So one thing that happens in these collision or interaction kind of problems is there's always a time involved, a delta t. How long did the interaction take place? Pushes scent with force F for time delta t from VI to VF, right? That's what we have here. So what we want to do is look at that in time and say, okay, here we go. Let's plot. You often want to think about this in these problems, is the force versus time, right? So at first, scent was going along, top bar, nothing's happening. She sees it behind her, but she can't speed up. And then the avalanche hits her like that, pushes her for a while, and then it stops, right? So this is the force of the avalanche on scent right there. Okay. So what we know is this is constant force. So we can just use this equation. We don't have a varying force because I plotted it. It's constant. I mean, it varies in time. It goes from 0, flat at 0, flat at maximum value, flat at 0. But if you just consider delta t here, it's a constant force. Right? So we say then we could calculate J, which is equal to delta P, which is equal to F delta T. And you can see what's happening. F delta T is the area under this rectangle here. And you also know it's probably an area under a curve because that's what that is, right? The integral of f dt, if f is some function, is just the area under the f dt curve. Okay. So let's throw some numbers in. Here, I made some up. And so let's see, it pushes her. So a problem won't say F is equal to this, right? It'll be words, right? Pushes scent with 300 newtons for 5 seconds. For 5 seconds, and she's 60 kilograms. It's probably bigger than that with all those gear on. Okay, so we want to know, what is the impulse? So calculate the impulse. See if you can do it on your own. Maybe even get the vector part right. We'll do harder ones soon, I promise. Can you clarify what, so while you're working on that, let's clarify what J is. J is just the symbol that we call the impulse. Right? It's literally equal to delta P. So when you're doing a problem, you might forget to write it as J. You might just call it delta P. It's just for some reason, we gave delta P its own name and its own symbol. And it's J. That's all it is. Literally equal to delta P. All right, so if you're doing this one, you say, well, it's the force times the delta T. And therefore, it must be, is delta P like, is acceleration? No, it is literally delta P. If like J is not acceleration, J is just literally the final momentum minus the initial momentum. So here, let's look at it and see if we can figure it out. What is the impulse in this case? Okay, we don't do it in this problem, but in a little bit we will. Well, it's just 300 newtons times 5 seconds. It's 1,500 newtons, or 1,500 kilogram meters per second. Right? That is how much her momentum changed. Right? You can also see it in the units, right? So if impulse is F times delta T, that's newtons times seconds. That's kilogram meters per second squared times seconds. So it's kilogram meters per second. But that's just a momentum, right? Mass times V. Okay? So in this one, unfortunately, it would have been good. Oh, no, but I can count. Though the next part is, what is her impulse? And also, how much does she speed up was the other part. Maybe this will help. Did she speed up in meters per second? Okay, think about that for a second. See what you get. So, she had some initial velocity, say, but how much faster was she going after the avalanche was done, but before she teleported to her bedroom? I would have to say it's 1,500 equals delta P, right? So that's the mass times delta V. If it's mass times velocity here, right? So here her initial Pi is her mass times Vi. We're in one dimension, so I'll leave the vector stuff off. And here, Pf is that same mass times Vf. Then you can see that delta P final minus P initial, equals what? Mass times V final minus mass times V initial equals mass times final minus initial, delta V. So delta P equals mass times delta V. And delta P is the impulse, right? So it's basically just 1,500 divided by her mass would be the delta V. Her mass was 60, so delta V. So I got what? 225 meters per second. So that's pretty fast. Unrealistic numbers. Sorry, I'm not a writer, so you know I can't. Delta V is 25 meters per second. That's about over fastest twice. Twice as fast as like a world-class sprinter doing the 100 meters. Okay? All right. Now, does she conserve momentum when she teleports to her bed? That's the real question. I don't know. Because once when I was playing Dungeons and Dragons in 1984, a pretty vehement argument broke out. Because like a monster attacked us and we cast a freeze spell and it stopped. And we're like, well, while it's frozen, let's put it next to this cliff. And then when it unfreezes, it'll just fly off the cliff. But does it conserve momentum after the spell runs off? It's a pretty deep discussion. It went on for a while. I'm still thinking about it. Okay, it's clearly still bothering me. Okay. Let's see. Now what we want to look at is microscopic impulse. All right, microscopic impulse. So how are we doing on? Oh, that's the first half. Okay. So this is really about microscopic impulses, the detailed force versus time, right? In reality, we don't really always just have a constant force. You know, if an avalanche hit you in the back while you're on a snowboard, is that going to give you a constant force? Probably not. Okay. Oh shit. This is the departmental. That tastes like William Marsh Rice right there. I think that might be his original breath in this thing. This is the departmental beach ball. Okay? And it's got a few vectors on it from some inferior teaching that was done before today. But I'm going to use it to demonstrate this momentum concept. So we're going to give this an impulse, right? So when you hang something like this, it's a way to make it weightless in a sense. If we want to see how does this move in 1D without any interference, just under its own sort of, inertia, see, it's mostly 1D free here. If you get far enough over, then of course it pulls it back. So anyway, here we go. So there it is. So we're going to shoot it with the big gun, and we're going to apply an impulse to it with the bullet. I meant to come practice this last night, and I didn't. So this is the first time I've ever shot that with this bullet, so it might fly off and hit you guys. So I was going to practice it and see if it hits you guys, so just look out. Watch your face. Can you also use P equals ma delta t to solve for acceleration, then for velocity too? Probably not, because we're doing something else. We'll get to it. Okay, so let's see. Watch if we apply impulse, does it move? You've got to be kidding me. Oh, there may be aerodynamic problems, and it may be impossible to hit it, because it may feel the... Let's find out. It may go around it every time. I didn't think of that. Wow. I really should have done this ahead of time. Wow. We're seeing aerodynamics at work. Check this out. There we go. Oh my God, I'm sorry. Okay, I didn't think it would fly off that fast. Okay. You saw it go, right? We won't do that again. Sorry. You're okay? Okay, you're okay. Wow. If that had hit you in the face, I would really be worried. I'd really be concerned. Okay, let's take this down now. We set that up ahead of time, right? See, that wasn't an accident. Okay, so what we had here is we had a beach ball like this, right? And we had a bullet like this, right? So this had initial P1 initial, and this had initial momentum of P2 initial, which was 0. They were just sitting still. This was going like that, right? So it's got its vector. This is just sitting here like this. And of course, after they hit, we're going to pretend it remained in one dimension as it was supposed to. And this kind of came to the side, and suddenly this had P2 final, and the bullet bounced back like that. So we had P1 final. So the situation looks something like that. Before and after. Almost like an energy problem in this case. Okay, so let's make a plot of what the force versus time probably looked like. And the reason I have all these soft things out is you can imagine when the bullet hit, it didn't apply a constant force, right? It went in, and the things like a spring, and the bullet is elastic, like we talked about, like a spring. So at first the force is very small, and then it gets really big, and then it flies out again. So it's really not a constant force. It's like a peak force. It looks something like this. That's what really happens when two things crash into each other. Is things deform, they act like springs, and you get some shape like that. So if we were going to do this, we would say, oh my God, we have to do an integral from T1 to T2. This is T1, T2, of whatever that function is, right? This is f as a function of t. I'll go ahead and put a function of t. Don't think they're multiplied. Of that function of time times dt, right? And that would give us the impulse. But we know that's actually the area under the curve, is our sort of a geometrical interpretation of that, right? So what we do then in problems to make them doable is we say, no, let's just think about the average force, right? Force is a function of time. We say this has some area under the curve. So let's do a lower area, but constant and for longer, like this, between T1 and T2. Right? Where this is the F average. Right? So then we can say J equals F average times delta T. T1 minus T2. And then it's constant. And it makes it easy, right? So what you do is you pick, or you set, pick, if you're choosing, set, if you're writing a problem, F average to make the areas equal. That's the idea, is if we bring this down, if we were to put F average up here, then clearly the area under the square would be bigger than the area under the peak. But if we start lowering the height, then eventually the area of the rectangle will equal the area of the peak. Okay? So there is some value of F average that you could set here that allows you to make this approximation. Okay? So in every problem we'll have you do, it's just going to be F average. Okay? I don't think, well, who knows? I don't want to make any crazy broad statements, but you never know. But most of the time, we're just going to make you do F average. All right? And one question that we'll deal with more on Thursday that you might wonder about here is, wait, which force is which? Are we talking about the force that the bullet applies to the ball or the force the ball applies to the bullet? So I'm not even going to write it down at this point, but remember, that's an action-reaction pair, so they're the same. Okay, their directions are different, but if this is just the magnitude of F, the same area, the same impulse is being applied to this that's being applied to that. It's just here the impulse is forward, here the impulse is backwards. That's the only difference. Okay, but that'll be important when we do conservation next time. Okay? All right. Let's read this and just take it easy. Same integral to find the average value of f as you would to take the... So here's a couple questions. Why don't we do these rather than jump in, because we only have like 2 minutes and then we'll take a break. So here's two good questions. Let me see if I can figure out what they're saying. Excellent questions. I just don't understand. Let's see. Shoot. Oh my God. Don't you need the same integral to find the average value of f as you would to take the integral of f over the interval? Yeah, so the point is, if you get this f average, you don't have to do an integral. Oh, and also remember, this isn't a function anymore. So f average is a constant. So the advantage of having f average is simply that it's just a constant times delta t. So there's no integrating to do or anything. What's special is it's equal to the value that makes these equal. Okay? So it's always less than the peak f. So in problems, they'll just say find f average. A way we can make this tricky is, do you think the peak force is larger than f average or less than f average? It's larger, right? Because that's the way f average works. Let's answer this one. Excuse me, this came in earlier. Can you also use P equals ma delta t to solve for acceleration, then for velocity too? If this were the first 6 weeks, you could, yes. Right, so we can always tie this back to kinematics and do things by kinematics, but we're trying to show this new way of doing things with momentum, conservation momentum. Okay. Okay, all right, so let's take our quick break and then we'll talk about something. Okay, let's keep going. You guys are so happy and excited and loud. Okay, we're going to do, I forgot, I went and erased it. So we're going to do a quick practice problem based on the dart. All right, so let's go back and say that dart, and you're going to calculate it, and then everybody's going to get it wrong. We'll talk about why. That's what's going to happen. Okay, here we go. Just to build up your confidence, I'll tell you that. Okay, so let's say it was a 100-gram dart. Okay, and it was going at 15 meters per second here. No, I'm sorry. Oh, crud, I changed the numbers 5 times. It was going 15 meters per second, very fast, right, at the ball. And then it bounces back I had it drop down to 8 meters per second, right? So let's calculate what is J. See if you can calculate J in that case. Boom, boom. The whole thing for you there. Yes, F. It must be the mass. How many, wait, hold on. How many got 0.7 kilogram meters per second? Not quite. Yes, because you forgot that momentum is a vector. This is the most common mistake in momentum problems. That's why I made you do it and asked you to raise your hand. How many, let's see, so don't forget, I'm trying to decide if I'm going to write this here. Let's write this here. Don't forget that P with an arrow over it is a vector. Okay? So I'm sure many more people than raised their hand got 0.7. Because you said what we've been saying is J is m times delta V, and delta V is 15 minus 8. Right? But it isn't. We had a bigger change than 15 minus 8. We were going forward 15, and we came back 8. So the difference is 23. Right? So let's look at that in detail. What I mean is let's remember that this thing, well, here's the V. V initial was 15 meters per second, say I hat, if we wanted to write it in detail. And V final was minus 8 meters per second J hat. Right? If we wanted to put it on an axis and do it correctly. And then we know that J vector, let's say in the x direction, so we're doing one dimension in the x direction, equals what? It's equal to delta P in the x direction. We don't need the x's, it's one dimensional. Right? So the vector J is equal to the vector delta P. So that's a good question. At the break, what are they the same? So can I say an object has impulse momentum? No. So they're not exactly the same in that sense. The impulse is only the same as the change in the momentum. It's not the same as the value or the amount of momentum. It's the change over some process. Right? So like how much money you have is in dollars, and if you have a transaction, that's also in dollars. So how much money you have is how much money you have. A transaction is how much your money changes. So that's the sense in which they're the same and they have the same unit, but they're not really exactly the same. This one is a change. So J is delta P, so we would say, okay, what is that equal to? Then how do we get delta P? Well, it's P final minus P initial. Right? Changes are always final minus initial. Right? With a negative sign, right? Subtract P final minus P initial, okay? But then, to do a problem, often then we go to magnitudes. And then we put in the negative sign, right? When I said 8 right here, that's a magnitude. It has to be a magnitude. It's a number. The number 8 is not negative 8. It's 8. And you can say I put the negative sign in front of the magnitude to tell me it's going left. Or you could say the component equals -8. You can interpret that either way. So when we go to plug in here, we'd say P final, we could say it's the magnitude 15 and it's positive because it's going to the right, plus 15 meters per second. Right? Or you could say the component of the vector is plus 15. But then this minus is not saying it's going the other way. That minus is because it's a difference. So that minus has to be there. Right? This is the difference minus. You can have a change in momentum and go forward and not have these two be opposite directions. Remember Sint? She was going forward and she went forward faster. So both of her velocities were positive. Yeah. Oh, did I go backwards? No, it's slowed down. Yeah, 8 is final. 50, oh yeah, I just said the wrong number. Wait, final minus initial. Yeah, sorry, so I wrote these backwards. Final minus initial, so my notes are backwards. So final is -8, right? So we all agree, I could either say that's the vector component, thank you. That's the vector component is -8, or I could say it's negative and the magnitude is 8. Y is 8 meters per second, J hat, not I hat. Okay, so I've just totally blown this all over the place. Wow, I have them in different dimensions. Oh my God, okay. Well, this is actually what happened when it took a 90-degree turn and almost hit the guy, right? So it did actually go from my head to J. But anyway, I was just trying to be real, you know, okay. Let's start over. Let's start over. A simple one-dimensional problem. The bullet went forward at 8 meters per second in the x direction, so it's, I'm sorry. Okay, let's start over. The bullet went forward at 15 meters per second in the x direction, therefore that is plus 15 I hat. And it bounced straight back at 8 meters per second backwards, also in the x direction, also, so it's also I hat, but we put a negative sign on it. Okay, delta P is final minus initial, so the final momentum was -8 meters per second, right? We got to multiply by the mass, right? So -8 meters per second times the mass, which was the mass, we give you the mass 100 grams, 0.1 kilograms I hat. I'm really just trying to illustrate the negative sign. And then this is what I'm trying to say. This negative is not because it bounced the other way or initially started the other way. That is just due to the definition of a difference, right? Difference is final minus initial. So now we put in this speed, 15 meters per second. Magnitude, it's positive. So we can say minus positive 15 meters per second. We've got to multiply it by the magnitude, or by the mass, kilograms. And then that's also in the I hat direction. Okay. So you can see this is how we ended up using 23. So it's actually negative, I should have said. I didn't define the positive direction yet. Oh, yeah, I did. So this is 8 minus 15, negative 23 times 0.1, minus 2.3 kilogram meters per second, also I hat. Right? Okay, so unfortunately I sort of flubbed that in the middle and maybe confused you worse, but if you got 0.7, think about why it's 2.3. It's because often in collision problems things change direction, but not always. Okay? Think about Sent getting hit from behind by the avalanche. All it did was speed her up. She didn't have a change in direction. So you don't have to have a change in direction. Okay, before we do the next problem, just while we're sort of, just to break up the problems, we'll do, the next problems are much more complicated. So let's take a quick break and look at Newton's second law and see if what we're learning here has told us anything more about the Principia here. Because if someone was asking, can we use impulse equals ma delta t with kinematics? Well, you kind of can, because that's kind of what Newton was talking about here. So if we look at a second law, what was the second law say? Oh, there's Latin, there's there we go. There's that. Oh, we didn't watch that. Oh, wait, crap, where'd it go? Oh, I didn't put the translation of the second law. Where's the second law? Oh, no, I have to translate it live. Oh, God. Oh, never mind. The second law is related to momentum. Never mind. Let's see. Let me just write it down. Newton's second law. We don't need the words. All right. So here it is. Here it is in Latin. I really do need someone to translate it now. The modus proportional to the life of the mortician was impressed by the fire, and the second line, I don't know what the hell it's saying. Okay. So Newton's second law is sum of the forces external equals ma, but he didn't say that. He didn't say, oh, the force is equal to the sum of the forces is ma, because we could look at this and say, what is A? A is mass times dv dt, But if you know a little bit about derivatives, you know you could put a constant inside of there, right? Constants just go in and out of a derivative. They don't matter. So we could say it's dmv dt. Ooh, what is that? That's dp dt. So if you read actually what he said is he's really talking about the state of motion again. He says the state of motion changes when there is a force impressed thereon or something like that. Okay? So technically, this is an approximation. Technically. Because you could imagine a case where mass is changing. And then if mass isn't constant, you have to have a term of v times dm dt plus m times dv dt. So you say, well, if mass is constant, surely you throw that one out and you just have this, and that's just F equals ma. But in a sense, F equals ma is already an approximation. It's already incorrect. Okay? If you think this way, you'll mess yourself up and you'll get some weird inconsistencies, and it's because nothing can really change mass in terms of fundamental particles. Like mass is always constant. So if you start changing the mass of something because it's like leaking sand, it's sort of a made-up homework problem thing. And it usually works. But you can turn yourself in knots over it. But I mostly just wanted to point out that really, you might see somebody write some of the forces. You might see a coffee cup. This is some of the forces as dp dt rather than ma. And this is the reason. It's really what he meant. Okay. That was the useful sidebar there. Here we go. Okay. It was worth it. Okay. Okay. Let's see. So we've done that. Now we're going to analyze, we're not going to shoot it, we're going to analyze this case here. And we're going to show how much easier it is to solve a problem by momentum than it is by kinematics. Okay, we're going to solve it both ways, and it's going to involve a spring. It's going to have everything we've been doing. Oh my God. Let's just do it on this board here. Okay. What we want to think about, hold on, let's see what we got here. Yeah, what is written after the force? MA. External. Remember, it's the external forces. Yeah. What is the subscript for Newton's second law? MA. External. Yes, it's external. EXT. We'll talk a lot about what an external force means Thursday when we do conservation. I think we kind of defined it when we did Newton's laws, maybe not. Okay, so let's ask this question. What is F average of the Nerf gun? I mean, if you think about what's happening inside the Nerf gun, is when I pull this back, it's a really big spring, you know, and then the spring is pulled back and you release it and it releases the spring and it pushes a bullet forward. So it's giving an impulse to the bullet, right? The bullet starts at v equals 0, it comes out really fast, it changes momentum, something applied a force and gave it an impulse, and there's a spring in there. So we're going to calculate that. We're going to figure out what is the average force of the Nerf gun. Okay, so at first, you've got the spring really tight like that. You've pulled it back. Okay, and then when it releases it, it's kind of like this. There's the little thing that the bullet sits next to, and it's like that. Right? I'm going to ruin all your childhood memories by applying physics to them. That's what this class is about. Here we go. So now on this axis, we have an x-axis, right? And it's best in this case, since the bullet is going to be released, to call this the origin. All right? Because the thing will only go to its natural length. Remember how a spring had a natural length? So it'll go out to that point, and then it'll pull away. So this is kind of like if you just put the bullet in and didn't pull the spring back. And this, we're going to call, crud, I called that, well, we're going to call this negative L, because that's what my notes already say. I wasn't going to call that L naught. Negative L is how far back is how far the arm is that you pull it back to tighten up the spring. Okay. And we're going to say when the bullet flies through this path, it flies through in delta t. Okay. This is not a time axis. This is a space axis. I'm just telling you, when it goes from one to the other, you can do it like that. Might make more sense than making you think it's part of the axis. Is it takes delta t to get from one place to the other. Right. Okay, these are all about the subscripts. Okay. All right, what else have we got here? What else do you need to know? So let's give you some values. Now the spring has a spring constant K. Right, so we're going to say it's a very stiff spring, 600 newtons per meter. That's not actually that stiff. L, how far we pulled it back, is 0.25 meters. Okay, it's going to fly through in 0.2 seconds. And it's going to come out with a velocity of 19 meters per second. These are all the right order of magnitude. I didn't measure it. Maybe next year we'll measure it all. And the question is from that, now you know, based on how springs work, that this is not going to be a constant force, right? Here the force is 0. As you pull it back, you get more and more force. So the force is changing as it pushes it. But we want to ask the question, what is F average? That's what we're trying to get for the spring, okay? So just as a little bit of a review, we'll first try to do it with Newtonian kinematics. Now to do it, we have to do a little bit of old stuff that we've already done and jump ahead to some stuff we'll eventually do. So don't panic if this all doesn't make perfect sense. If this isn't really the momentum part. After this, we'll do the momentum part, okay? But still, if this made sense to you, it would mean you're getting there. You're getting there. Let's see, we want the average force. So the first naive thing you might think is, oh, well, that's not hard. We know Hooke's law. We talked about how forces vary. Here's where it releases, no force. Here's minus L, la 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 la, do 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 do, like that. Right? So it pushed really hard here, and the push went down and down and down, and that must be K times L. Right? If we push a distance delta L with spring constant K, it must be pushing forward KL right there. So we even know this value on this axis, right? KL. So you'd say, well, if it's just going down, then the average value must be 1/2 KL, right? If it's going down, or if we did the area, it'd actually be a little lower than that, right? It'd be down here, so 1/2 KL. So we could do that geometrically, but this is wrong. But that is F versus X, right? The definition of the impulse is it's the area under the FT curve. And the definition of the average comes from thinking about the FT curve. We need F versus T, right, to be able to do this. So that means this is a lot harder, right? So we say, okay, well, let's try to do it. So let's see. We know sum of the forces equals MA. We know minus KX equals MD2X dt2. And then how did we solve that? We guessed, right? This is from whatever it was, 2 times ago. And we all guessed. And, well, me and Dr. Stenson, who was the third person? Shams guessed. And we guessed a bunch of stuff, and I said, that's how you do it. And then the answer is, when we get to harmonic motion, we'll know that the answer is like this. Once you guess properly, the answer would be L sine square root of K over M T. The answer is a sinusoid. Okay? Interesting. So now you got to start thinking carefully about physics problems. Okay? That's why we're doing this problem, is it's going to make you think carefully. Does the motion of that look like a sinusoid? Does it go back and forth? Is this sinusoidal solution even relevant to our problem at all? I don't know. Let's draw it. Let's see. So is a sine relevant? So if this were some crazy hard pledge problem, this is the thought process you'd want to go to. You'd want to say, well, let me plot a sine. It's like that. Okay. So we said we're not starting at the origin. We pulled it back to here, and we released it. Okay? So if this were a sine, it would do this. So we pulled it back to the lower position, and then the reason it doesn't continue to do this motion is because the bullet comes off. Right? The mass is gone, and it's not designed to let it further extend. Right? So the mass of the bullet is important, and then it becomes detached. So really the only relevant part is from when you pull it all the way back to 0. So you could look at this sine and say, okay, this is actually correct and part of the problem from here to here, from initial to final. Because it is just like this simple sinusoidal motion in this one part, because when you're moving in sinusoidal motion, when you come all the way to the back, you stop and go the other way. Well, we're starting from a place where it stopped, and it's going the other way. Right, so I would argue that this is actually exactly relevant right here. It's basically a sinusoid from there to there, executing that sinusoidal motion. Now that is not F versus T yet. It is X versus T. All right. So how are we going to get F versus T? I just thought of an easier way. Well, let's do it my hard way. Then what you would want to do is get the acceleration. So you'd say, okay, I need the acceleration plot. All right, so how do you get acceleration if you have this? You take two derivatives. Okay, the first derivative is sine to cosine, and you pull out a square root of km. The next derivative of cosine, the negative sign, you pull out another square root of km, and you get a equals lk over m, and it's negative sine square root of k over mt. Again, this is getting into harmonic motion we'll do later in the semester. I just want to show you that you just take two derivatives, which you did learn, in the 1D kinematics part, and you get that. Okay? I took two derivatives. This came out twice and multiplied. So square root of k over m times square root of k over m is k over m. And then the L is still there, and there's a negative sign. So if you were to plot that, that's now just negative sign. The negative sign makes a negative sign. I apologize, I did not make up English. We could just go back to Latin, I guess. Oh my God. What a horrible sign. There we go. So what this will tell you, here's the acceleration. And this is kind of like some homework problem, I think, or maybe it was on the pledge or the exam. The acceleration here is actually the maximum value. Right? So the biggest force forward, the biggest acceleration forward is when you pull it all the way back. Oh yeah, that's right. The biggest force forward and the biggest acceleration is at the very beginning. And then it falls in time. Okay? So if we wanted to turn this into the force, we just put m in front of it. And now we're plotting the force. Right? So basically, this is the force versus time. It's a sinusoidal thing dropping, like that. So let's plot that bigger. All right, so that means that it's some maximum value, and it does that. All right, so here is the impulse, because that's equal to the integral of the force as a function of time, which we didn't write out. We could have. We just put an m right here. Lm k over m sine square root of k over mt. The m's cancel, and it's kl. That's Hooke's law, right? The force is minus kx, and it just oscillates in sign. All right. So this is k times l. Okay, we're making it positive because we pulled L negative. That we could put negative L in, and that would cancel that negative, so it'd be positive. So KL, and it decays to 0 when the thing becomes detached, right? So this is initial, and this is final. Or in this case, here, initial and final. All that work. Oh my God. What does that say? Oh wow, I got a picture of my own board. Wow. I thought I was into fancy things. But that is F. You need, that's a very bad D. There you go. You need that. Okay. Okay, so what are we doing here with our lives? What are we all doing? I don't know. T initial, T final. I mean, at least you're paying to be here. I'm not even paying, right? I forgot what we're doing. We're trying to get F average. Oh, so we need to know what is the average value of a sine. Well, the average value of an entire sinusoid is 0. But the average value of half of a sinusoid is 0.637. Everybody knows that, right? Yes, okay. You could do an integral to figure that out. But basically, the F average is 0.637 times KL. Again, this isn't the way we're really doing it. I'm just showing you how hard it is with kinematics and forces. This is a little beyond what you would do. We could give it as a pledge, I guess. Right? So you just have to know that the average value is 0.637 times KL, and then you just multiply that out. K, 600 Newton per meter, L, 0.25 meters, 95 newtons. All right, that wasn't so bad. Look at all the kinematics we just did. All right? Now, who's excited to do it with impulse? Okay, good. Okay, here we go. This is how much board we need. I'll do it in this much board. No, I want you to be able to read it. I'll do it in this much board. Let's do the exact same calculation with impulse. What is impulse? Let's see. What do we know? We know that impulse is equal to the average force times delta t. So the impulse we know is the change in momentum. Started from rest, and it went to 19 meters per second. So we take the mass, right? So let's see. We know that J equals F average times delta t, right? This is where we don't have to do the integral. The constant force. It's just J equals F average times delta t. What is J? J is delta P equals S average, F average times delta t. What is delta P? It's mass times final velocity minus mass times initial velocity. Or, if I may factor something in front of you, if you don't mind, mass final velocity is 19 minus 0. So there it didn't rebound, it just went. The mass was 0.1, right? 0.1 probably. Oh, I didn't give you the mass. Mass is 0.1. Yes. Kilograms, 100 grams. 0.1 times 19 minus 0. There's delta P. Wouldn't we take the integral of a fourth of a sine curve and not a half? It's the same thing. You get the same thing because they're symmetric. The integral of each side is 0.637. Mass times that equals the thing we're looking for. And what was delta T? 0.02 seconds. 0.2 seconds. Oh, I lied. It's 0.02 seconds. We actually need it this time. So somebody solve that. What do you get? Correct. You get 95 newtons. F average. You get the same thing, right? So that's what's great about doing it with impulse, is you don't have to think about the details of the force. Here we actually did. When I said we'll never think about that crazy curve, we did. Look how hard it was. Okay, we didn't like that. All we had to do was impulse. Now, of course, I used a set of numbers that were consistent. I solved it both ways, and all these numbers, it was 19 because of all the detailed kinematics. But in a problem, you would really just have to use the impulse way, where it would say solve for the average force. Okay? If this was like sophomore physics, we would make you do the integral of the quarter of a sine wave or something like that. All right. Okay, for the last few minutes, I've got one more thing to show you here that will help you understand this a little better. And that is, I have bad news, which is that, let's see, I was overlooked for the Nobel Prize this year. I didn't think I was going to be here today. I think when I sent the check in, I forgot to convert it to kronas or something. But the winners were Arthur Ashkin, Gerard Mural, and Donna Strickland. A big optics person. I think she's something in the Optical Society of America at the moment. And she's the third woman to win a Nobel Prize in physics ever, which is pretty good. I'd be a little intimidated by being in the company of Mary Curie and Mrs. Geppert. I forgot her last name. It's hard to say. But it's very exciting. And the first one, though, so the second two, Strickland and Morrow. Oh, and also Strickland is an associate professor. She's not even full professor yet. So I have a feeling that's going to get turned over. It may be the most rapid P&T committee decision ever. I don't know. But Arthur Ashkin did something exactly relevant today, something with momentum, right? Trapping particles. If you read, you can read the scientific background of a Nobel Prize win, and it's really sort of scientific American level. Like, you can read it and understand it. And it's also really the point of it is it's justifying all the people who didn't win, right? So if you see anybody cited in one of these documents, they're like really pissed off because it's the point of the document. It's just to educate the public. But this is a figure from the document, and it's about how you can use light to trap a particle. Somebody's... Okay, we'll get to that in a minute. It's how you use light to trap a particle. So you can, if you just shine a laser beam on a little dielectric particle that causes refraction, the particle stays inside the beam. We're going to do every aspect of this before the end of the year. We're going to do geometrical optics and all kinds of stuff. So today I'll just describe a little of that, but I want to show you why the particle is trapped in the beam. It's exactly what we've talked about today. It's impulse. It's literally impulse. So let's say here's the particle, right? And a laser beam is not uniform in space. If it was, it'd be really big, right? A laser beam is this teeny little beam. For a laser pointer is small. So if you were to look at like how bright is it versus position, it's like a curve like this, right? It's like, it's like that. Right? So say your particle and your beam are about the same size, whatever. So now light, you have this ray tracing, maybe you've seen before. So you could bring in light like this. And if the particle's in the middle of the beam, you have the same amount of light here, and you have the same amount of light here, right? Like that. And then light, when it goes into a dielectric like glass, it falls to the normal. Like that, and that, and then it is away from the normal like that. So you get something, I mean, I haven't drawn it perfect, but something like that. Okay, the light's going to come in. Now, a long time ago, there was an argument of whether light is a particle or a wave. Well, it's a particle. Newton won, light's a particle. It's actually a bunch of little photons coming along like that. And those little photons turn like that. What does that mean? They had to have had a change in momentum, because they actually do have momentum. Right? Light carries momentum with it. That's why it can push things around. One question is, do we still have pledge problems due Monday? No, we've never had pledge problem. I mean, we've only had one pledge problem so far. So there's no pledge problem. The homework that was due, maybe the calendar says there's one. There's one. The homework that was due Wednesday, I'm moving to Friday. Okay, so what we got to think about here is, what is the, we're going to call this A on the left and B on the right, and we'll say it has an initial momentum, P, A initial, and then here's the final momentum, P, A final. Because all the photons that go in come out. They just get bent by the particle. And PB looks like this, a momentum, B initial, PB, a momentum, B final. So let's think about what impulse it would take to create that, right? JA equals delta PA. How much did this momentum change? Final minus initial. So we draw the final vector like that, and then we add, oh, so no, A went the other way. A goes this way, right? And then we add the negative of the initial vector like this, like that. So A had an impulse that way. There's JA, there's delta PA, or whichever one you want to call it. So the photon got pushed that way. And then we do B, J, B equals delta P, B. And it looks like this. So delta PB is that way. Final, initial, delta P, or JB. So we say the photons felt a kick. The photons felt a kick like this. If you vector add those, the lateral parts cancel, and it pulls back a little bit. Right? So that's total J on the photons. But if every action there's an opposite and equal reaction, what do you get? Oh, the bead was pushed forward a little bit. Okay, so what? Who cares? I know. No, that was the kind of question you're not supposed to answer. Now, let's put it over here. What if the bead sort of drifts to the side and starts to try to leave the beam? Now it's bright here. Okay, now you can see where we're headed, and it's really weak here. Right? A lot of photons here, just a few photons there. A lot of photons giving me this kick, and just a few giving me this kick. Okay, so which one gave which kick? The strong one was B. We get a strong kick this way on the photons. We get a strong kick this way on the particle. And the weak one was A. Right? Strong kick, weak kick this way. So you see what happened? JB is bigger than JA. And which way is the net force? That way. So if the bead tries to move out of the beam, the impulse from the light pushes it back into the beam. And if I drew it over here, it would push it back into the beam. Right? So this is how you trap particles. Then if you focus it with a lens, it does the same thing this way. So all you do is focus light, and you have a three-dimensional trap for dielectric particles, and it's used in biophysics, and you win the Nobel Prize. The end. Okay, we'll see you Thursday.